You may remember last video we talked about a couple of different kinds of bonds. We talked about ionic bonds and metallic bonds. I'll spell ionic here. And ionic had to do with ions, with these elements that tended to lose electrons or gain electrons, and that's how that bond was formed. But in covalent bonds are a little bit different. Covalent bonds are where the electrons are shared. Now, one easy way to remember about covalent bonds, you may remember ionic bonds were mostly metals. It's not the case with covalent bonds. Covalent bonds are almost always non-metals. Non-metals. So even if you kind of forget the sharing and the ions, if you look as to whether they're metals or non-metals, that'll kind of let you know whether it's going to be ionic or covalent. And you guys may remember that pretty much from here over this way is metals, and from here over this way are non-metals. Now there is an exception. You do have hydrogen, which is a non-metal also, but all of these over in here are metals. So the ones that have to do with these are in most cases ionic. The ones that have to do with these are in most cases covalent. Now you may remember there was another kind, metallic. The metallic bonds generally had to do with these transition metals right in here. So metallic in the middle, ionic, they had mostly to do with these alkali and the alkaline earth metals. And the covalent will have to do with the non-metals here and with the hydrogen over there. So that may be the simplest way to remember the difference between ionic and covalent. But anyway, covalents share electrons. They don't tend to have too much ionization going for both of them. Now, one thing about covalent bonds, you often have them together. Chlorine. Chlorine, let's see where chlorine is. Chlorine happens to be right here. It is a non-metal. It's also a halogen. So since it is a halogen, it is going to have a negative charge. Oh, my bad, it's going to have a positive charge because it tends to get all those ions that are from like over here in sodium and all. But since it needs one, it often will get another one from the other chlorine atom. So that presents a covalent bond. It doesn't need the sodium or other kind of element in which to become like a neon gas. My bad, become like a noble gas. It forms a covalent bond with itself. Now when that happens, you signify it by having a single bar between them. In this case, it would be Cl, and I'm writing this, and sure enough, I notice that I have this off to the left. Cl, Cl, and sure enough, here it is. That's how you would indicate a covalent bond between two chlorine atoms. Now notice what you have right here. You have two bars. This is going to be a double covalent bond. And let's see why oxygen would need a double covalent bond. I think I better erase some of this. See, where is oxygen? Oxygen is in this column. Notice where the chlorine was. Chlorine needs one electron. So since it got that one electron, it would be positive. Am I saying that right? It has 7 in its valence shell, so it needs that one electron. So when it gets that electron, it's going to be negative. Oh, sorry about that. I said that wrong earlier. But anyway, here it's going to need 2 electrons. It's going to need 2 electrons. So instead of joining with one of these metals over here, it sometimes tends to form a covalent bond. It will be oxygen, like oxygen here, except instead of giving one of the electrons, it will give two electrons, like two O's, and will share two X's. So oxygen and all of those in this column, whenever you have a covalent bond, they will have two lines between them. All those in the halogens in this column will have one line between them. So you have a single covalent bond, a double covalent bond. Is it possible to have a triple covalent bond? Of course it is. All those in this column. All those in this column, you have triple covalent bonds because you need the 3 electrons. So if you have, say, nitrogen, we'll just use the first one. Boom, boom, boom. That would represent a triple covalent bond. Now, the farther over you get this way, the more into the metals you get. So you wouldn't be talking about Bi having triple bonds because it's a metal and it would not form covalently. In fact, these metalloids, I wouldn't suspect that they would either. So going across the top is pretty much the only way you will get those covalent bonds. So that tells you a little bit about those covalent bonds and the single line, the double line, oh, here they are right here, and the triple lines, single bond, covalent bond, double covalent bond, and triple covalent bond. The more lines, the stronger the chemical bond. You may remember we talked about chemical bonds last video. The more lines, the stronger the chemical bond is. Let me look back on my notes and see what I have as far as anything I have left out. Okay, when electrons are shared equally, in other words, when you have the same elements, Cl, Cl, OO, NN, anywhere, any covalent bond where you have the same element that is sharing the electrons, it's going to be nonpolar. Now, what that means is, on either side, these electrons right here, they're not going to be more attracted to one side or the other because you have the same weight that is here as you have here. The gravitational pull, you might say, is equal. It is nonpolar. These are kind of equivalent right here. But you can probably imagine that there is something called a polar covalent bond where you don't have the same element there. When two different atoms share electrons, then you have a polar covalent bond. Shared neutrons are attracted more to one nucleus. And we have a very simple example here, water. Hey, is water with metals? No. Water is with nonmetals. H is a nonmetal. O is a nonmetal. So you can suspect, even though you might not understand the ionic and covalence difference, if you're talking about nonmetals, you're going to be talking about a covalent bond. So water, that's a covalent bond. Sugar was a covalent bond. Any of those bonds you can have between hydrogen and all of these right up in here. Any bond you can have between there and there, those are going to be covalent bonds. So here you have a larger nucleus here. So these shared electrons are going to be more attracted here. And these shared electrons are going to be more attracted here. Now keep in mind, that gives you a little bit of a charge. Gives you a little bit of a charge. So since you have a little bit of a charge, in fact, you can see kind of the charges over here. Since you have a little bit of a charge, that means you have the polar aspect to it, kind of like a magnet. Pardon me, it has polar aspects to it. So a polar covalent bond is with different elements. A nonpolar covalent bond is with same elements. Now, something else that you will find is that some compounds act both ionic, like ionic and covalent bonds. Both ionic and covalent. Let's see some examples. These are called polyatomic ions. So what you have here are common polyatomic ions. Let's see where these are. C, H, and O. Where are those on the periodic table? C, H, and O. Yeah, these are nonmetals. That's a nonmetal. That's a nonmetal. That's a nonmetal. So when you get them together, they're acting covalently. However, they tend to have a negative charge, because what happens is it wants to get one electron. So you can still have all these combinations and still not have it to where it's perfectly balanced. The C's, the H's, and the O's tend to get together and form like this, but they still need an electron. So since it wants to grab an electron from another atom, then it's going to often have that negative charge because it's going to grab another electron. So since it has a negative charge, that makes it an ion. So you know what can happen? It can then form an ionic bond with something that has a positive charge, like this. Ammonium has a positive charge. So it could form with that. So it would be formed covalently, like this, the C's, the H's, and the O's, and then ionically, like this. So as you look through all of these common polyatomic ions have these positive or negative charges. And you can see an example right here. Well, let me check my notes here. All the covalent bonds will look to form an ionic bond to make itself a neutral compound. So all of these that have the negatives and the positive here, they definitely want to be neutral, and that's why they continue to act as ions. So you put parentheses around an ion here. But do you notice the difference between here and here? You don't have the parentheses around these. Now keep in mind, these are ions here. These are polyatomic ions because the P and the O have already matched together. The N and the O have already matched together. But here you have parentheses, here you don't. The reason is because of this subscript 2. The NO3 is a negative. It's a negative 1. And the Ca2 is positive 2. So you need 2 NO3s. So whenever you need parentheses is when you need more than one of that particular atom. Okay, I think that's pretty straightforward. You can see from here where cases where you'd use parentheses. Here you have 3. Here you don't have 3. You don't have any extra of this SO4 right here. Okay, one thing I need to get through before we run out of time is the names that end with ATE and the names that end with ITE. Some polyatomic ions names relate to their oxygen content. An ATE ending is used to name an ion with more than one oxygen atom, and IT has less oxygen atoms. For example, here's nitrate. Nitrate is O3. The nitrite would be O2. The phosphate would be O4. The phosphite would be O3. So if you look right here, here has 3 and here has 4. Which one would be the ATE? The one that would end in ATE would be this one. The one that would end in ITE would be this one. Hey, I hope you've learned a little bit about these ions and covalent bonding.